Hi! Did you know? Water covers approximately 70% of the Earth's surface, where approximately 97.2% of it is saline. Only 2.8% is fresh water. Fresh water is the primary source of human health, prosperity, and security. By around 2050, the world's population is expected to reach about 9 billion, assuming that standards of living continues to rise. The main requirement of potable water for human consumption will amount to the resources of about 3 planet Earth. Potable water is available in almost all populated areas of the Earth, although it may be expensive and the supply may not always be sustainable. Sources where water may be obtained includes ground sources such as groundwater, springs, hyporheic zones, and aquifers. Precipitation, which includes rain, hail, snow, fog, and etc. Surface water, such as rivers, streams, and glaciers. And to know more about the potable water sources, just keep on watching for further explanations.
Hi, my name is Yorando Ioni, and today I will be reporting about the potable water sources, which is a surface water. So, surface water is any body of water found on the Earth's surface, including both the salt water in the ocean and fresh water in rivers, streams, and lakes. A body of surface water can persist all year long or for only part of the year. Okay, so example for the surface water, as I mentioned earlier, that's including streams, rivers, lakes, wetlands, reservoir, and creeks. The ocean, despite being salt water, is also considered surface water. Surface water participate in the hydrologic cycle or water cycle, which involves the movement of water to and from the Earth's surface. And the precipitation and water runoff feed bodies of surface water, evaporation and seepage of water into the ground, and also, on the other hand, cause water bodies to lose water. Water that seeps deep into the ground is called a groundwater. Alright, so you may ask if what's the differences between surface water and groundwater, how they're related. So surface water and groundwater are reservoirs that can feed into each other. So basically they are both related. And while surface water can seep underground to become groundwater, and groundwater can resurface on the land to replenish surface water, springs are formed in these locations. There are three types of surface water. This is perennial, ephemeral, and as well as man-made. So we need to differentiate what are those three. So first, let's talk about perennial. When we say perennial, this is basically a permanent, and of course, surface water persists throughout the year and replenish with groundwater when there is a little precipitation. And the second one is ephemeral. From the word itself, that is a semi-permanent. So in this case, surface water exists for only part of the year, and ephemeral surface water includes small creeks, lagoons, and water holes. And the last one, which is the man-made, from the word man-made, so this is basically found in artificial structures such as dams and constructed wetlands. And since surface water is more easily accessible than groundwater, it is relied on for many human uses. And it is an important source of drinking water and is used for the irrigation of farmland. So in 2015, almost 80% of all water used in the United States came from the surface water. Wetlands with surface water are also important habitats for aquatic plants and wildlife. The planet's surface water can be monitored using both surface measurements and satellite imagery. The flow rates of streams are measured by calculating the discharge, which is the amount of water moving down the stream per unit of time at multiple points along the stream. So monitoring the flow rate of streams is important as it helps determine the impact of human activities and climate change on the availability of surface water. Keeping track of vegetation around bodies of surface water is also important. And the removal of vegetation, either through natural means such as fires or through deforestation, can have a negative impact on surface water. And loss of vegetation can lead to increased surface runoff and erosion, which in turn can increase the risk of flooding.
Good day everyone, my name is Clifford Abarquez, and let's talk about groundwater. Groundwater is one of the main sources of potable water that is found underground within rocks. These water sources can be classified as protected sources or covered by stonework, concrete or other materials that prevent entry of physical, chemical, and biological contaminants. So nag-start ang groundwater sa uwan. Inig-uwan niya kay iyang water sa uwan muagtos sa yuta. Nig-abot niya sa yuta, ang tubig niya mo sink in siya sa ubos dito sa ground. Dayon inig-abot niya sa ground kay moadto na siya, maabot na siya sa aquifer. Kani si aquifer mo ni siya gitawag og permeable rocks kay siya ang motrap sa water nga gikan sa uwan mo sink in sa ubos para magpundo diri sa ground, padili siya mulahos, di siya mulapos dito sa earth. Unya nay uban no mangutan na nga bay ngano ang kanang mga lakes o river bay nga ilang tubig bay dili man mahubas, dili man mo sink in dito sa ubos, ngano man na. So explain na yung tamo ana no, nganong dili mo sink in sa ubos ang tubig sa lake o river kay tungod na siya sa porosity and permeability. So unsam din ni sila no? Unsam din ni sila porosity o permeability. So sila ang mo control sa flow sa water sa ground. Si permeable kay usa siya ka klase nga rock naa siya mga gagmay nga tiny spaces between the solid rocks and particles that allow water and other fluids to pass through and to be held within rock structure. So klaro kay no? Si permeable kay usa siya ka rocks nga nay mga bangag-bangag. Like sa picture no? Inig-drop sa water sa ground kay musink in ang water niya into ground kay tungod sa iyang permeable. Naigagmay nga space nga pwede musud ang tubig musink sa bottom. Mauna ang ubang area nga maabtan sa uwan, sa tubig sa uwan, musink in dayon ditso, moabot ditso sa bottom kay tungod sa iyang permeability. Unya ang uban kanang sa lakes nganong dili man na musink in kay tungod sa iyang porosity. Dili kayo kasink in ang tubig sa uwan, like mga tubig sa lake, kay tungod sa iyang permeability. Dili siya, wala siya mga tiny spaces nga moallow nga musod ang water niya padung sa ubos. Kay ngano man na? Kay low ang iyang permeability o porosity. Maong magpundo ra siya sa babaw. For example, rocks o mga lapok. Mga gravels, nagtesta mga gravels o mga lapok. So, ang gravels, gisud na to siya sa bucket. Hasta ang yuta, gisud na to siya og bucket. Ato siyang gitest. Gibubuan na to siya og tubig. Una, ang gravel. So, unsay resulta sa water? Ni sink in dayon siya sa bottom. Dayon, sa next, ang yuta. Gibubuan na to sad siya og tubig. Same ra ilang kadaghan nun sa tubig atong gibubo. So ang result sa yuta kay nagpundo ang iyang tubig sa babaw. Dugay siya ni sink in. So mao na gitawag nga ang rocks, gravel kay high porosity and permeability. Unya ang yuta kay dugay siya ni sink in, mo siya gitawag og low ang iyang permeability og ang porosity. Mao nagiingon maong ang lake ug ang river dugay ka sink in. Dugay ka sink in ilang ilang water. So makasabot kita sa river nganong dugay ka sink in ang ilang water kay tungod kay flowing man siya. Flowing. Nya ang lake sad steady ra, nya dugay ka sink in kay tungod low iyang permeability, no? Yan ay mo ingon ba nga bay ang sapa bay kay daghan man nagbato. Ano kay ingon mo ka nga low permeability na siya? So, dili. High permeability na siya, makaingon na ta siya nga low siya, dugay siya mo sink in kay tungod lagi nga flowing iyang water, no? Continuous iyang water. So kung dili na continuous iyang water, musink in dayon na dito sa ground ang iyang water, di lang ta kabantay nga wa siya hubas kay flowing man siya. Steady man iyang constant man iyang water nga nagflow, nagdagan-dagan gikan sa mountain padong sa ubos, mo nang dili siya mahubas, no? Pero actually kung ato gina i-deep gyud og study, musink in gyud na iyang kuan, high probability gyud na siya musink in gyud na dito sa ground ang iyang kuan, ang iyang water. So proceed ta sa next figure. So kaning next figure kay nag-emphasize ni siya kung unsaon pag-collect sa water, sa ground water padung sa surface, sa babaw, unsaon na to pagkuha nila. So ingani day duha ka pamaagi. So before ta ana, no, ako sa niibalik ang kaning aquifer kay siya mooy magkupot sa water para dili siya mo sink in dito si ubos. I mean magsteady ra siya, magpundo ra siya dito sa ground ang iyang water. So proceed ta sa wells and boreholes. Usually use a depth of less than 30 meters, although they can be as much as 30-meter deep. So ano man eh? Because kay naang ubang area nga init kayo, dugay pa kayo maabot dito sa ground. I mean, layo pa kayo gikan sa surface sa atong gitamakan padung sa ground. Layo pa kayo ang iyang water sa ubos. Lawom pa kayo. Mao nang naay uban nga 60-meter deep pa before matugkad ang tubig dito sa ubos. Example ng mga lawom kayo, no, kay kanang mga init siya, like init siya nga lugar, like tagsa ra mag-uwan. So naay mga pamaagi para makolek ang water sa ground para masaka sa surface, sa babaw sa atong gitamaka, no. Ang una kay ang well. Ang kaning well kay kato ni siyang murag tabay nga usually atong gamiton dito sa mga province, mga tabay siya. Kanang itagak ang bucket nya higtan og pisi, dayon ibitaron nya inigbitad na nanay sod ang bucket nga tubig. In large well, that casing needs to be constructed in concrete from the top of the well down to a minimum depth of 3 meter. Depending on the depth of the well, water may be drawn up by a bucket and rope. So mao na to kung giingon no. Kung laom na kayo ila na naitsahan og bucket nga higtag pisi para makuha nila ang tubig sa ubos. So ang usasad ka pamaagi kay high-tech ni siya no. Kay these are well that have been sunk with a drilling machine designed for a constructing water extraction boreholes. These machines are able to penetrate through harder materials that cannot be tackled by hand digging and cannot therefore pass through at least one impermeable layer of rock to a productive aquifer underneath. So, nindot ni siya kay sunk in naman na dito. So, kay muna ni siya puso ba no? I-pump na lang na siya nimo. At the surface, different type of pump may be used including hand pump like the figure 5 like katong gipakita na ko ganina atong bomba puso. For large boreholes in urban areas, electric or diesel power pump would be used. So sa laing lugar no, kay ilang gigamit kay kanang kuan na lang, kanang pump na lang, electric pump na lang. Kanang like kuan deep well gigamitan na lang siya og electricity kay para mo na mo collect sa water mo pump para mosaka ang water sa surface, dili na kapoy, di na mata magbumba-bumba. So high tech ni siya ang ikaduha. So maora to siya about sa groundwater. So let's proceed to other source of potable water.
Good morning everyone. My name is Arian J. Dueretes and I'm going to tackle about the last topic of our report, which is the rainwater, or 1. In regions where rainfall is abundant and frequent, rainwater can be a good source of water supply for individual families and small communities. The storage of rainwater is particularly important in areas with a long dry season, or where groundwater or surface water is difficult to obtain or polluted. The term rainwater harvesting simply means collecting or harvesting rainwater as it runs off from hard surfaces and storing it in a tank or cistern. The advantages of rainwater are it is free, relatively clean, and usually reliable even if it rains only once or twice a year. And lastly, rainwater harvesting system can be easily constructed and maintained at low cost. Although mainly found in rural areas, rainwater harvesting can also be useful in an urban situation. Rainwater can be collected in several ways. We have the roof catchments, the ground catchments, and the sand dams. And we're going to tackle first the roof catchments. So roof catchments. Rainwater can be collected from house roofs made of tiles, slate, or corrugated galvanized metal or equivalent. Pipes feed water from the roof and gutters into a collection tank where it can be stored until needed. If rainwater is used for water supply, it is important to ensure that it is not contaminated by improper methods of storage or by bird droppings and leaves from the roof that it is collected from. Rainwater may also be contaminated by pollutants in the air, dust, dirt, paint, and other material on the roof or in roofing materials. All of these contaminants can be washed into the storage tank or cistern. So example of a tank or cistern is this one. In this figure, rainwater is collected from the roof of this rural health post and stored in a covered water weight cistern. So this is an example of a tank and cistern. The various precautions in the roof catchments is that the tank must be completely covered and well maintained. Second one is the roof and gutters should be cleaned regularly, especially before the start of the wet season. it may be necessary to divert the first rainwater away from the tank so that dust and dirt are washed away. And the third one is the leaves and other larger debris can be prevented from entering the tank by placing a mesh screen between the guttering and the pipe that leads to the tank. The mesh screen will need to be cleaned regularly. The second way is the ground catchments. These are systems that collect and store rain falling on an area of ground. The amount of rainwater that can be collected depends on whether the area is flat or sloping, and on the permeability of the top layer of the ground. These systems require space, so are only appropriate in rural areas, where they can serve small villages and households for livestock and vegetable growing. So, in this figure, it is an example of a ground catchments. So, rainwater storage ponds in Amhara region. The third way is the sand dams. In arid areas where there is a dry, sandy riverbed and the rain falls once or twice a year, a collection system known as a sand dam can be used to store water. A sand dam is a concrete wall, a 1 to 5 meter high, built across a seasonal sandy riverbed. During the rainy season, a seasonal river forms and carries sand and silt downstream. The heavy sand accumulates behind the dam, while the lighter silt washes downstream over the dam wall. Within 1 to 4 rainy seasons, the dam completely fills with sand. However, up to 40% of the volume held behind the dam is actually water stored between the sand particles. The water can be abstracted from the sand dam via a slotted pipe buried in the sand that either passes through the dam wall or is connected to a simple hand pump situated on the river bank. So, this is an example of a sand dam in Kenya. That would be all, and thank you for listening.